Welcome to Study Loop.
Let's evaluate the given integral. So looking in the denominator, we see a third degree polynomial, and we should factor this if it factors, but it might not be obvious how to factor it. So what you might try here is the rational zeros test, which basically says if you have a polynomial with integer coefficients, which is what we have here, you look at all the factors of the constant term, in this case, just plus and minus 1. You look at the leading term coefficients, also plus or minus 1. And then you divide these terms by these terms. And these are all your possible rational number solutions. In this case, if we plug in x equals minus 1, plug that into the polynomial, you get negative 1 cubed, which is minus 1, negative 1 squared, which is 1, so those cancel, plus x, which is negative 1, and plus 1, so those negatives cancel out, and we get 0. So this tells us that x minus negative 1, or x plus 1, divides this polynomial. So we can go ahead and perform the long division to see the other factor. So we have an x plus 1 out here. We do our long division. x3 over x is just x squared. Let's go ahead and subtract. We have some cancellation here. X plus 1. X divided by x is 1. And then we get x plus 1, and we should get a remainder 0, and that's what we get. So this tells us that we can write the denominator is x plus 1, and then x squared plus 1. So much easier to deal with. And then once more, we go to this quadratic term, and we'd like to see whether or not that factors. So here you just check the discriminant, b squared minus 4ac. Where here, the a, b, and the c, these are just the coefficients of an arbitrary polynomial, quadratic. In our problem, we see that a is 1, b is 0 because there's no x term here, and then c is 1. So that in our problem, b squared minus 4ac is just 0 minus 4, which is negative. That tells us that x squared plus 1 does not factor, so we must leave this in the denominator for the partial fraction. So at this point, we're taking this integrand here. We just rewrote this using our division. And now we go ahead and do partial fraction decomposition. So the first term out here, non-repeated, and it's linear. So we have a over x plus 1. Since this quadratic did not factor, we already checked. This is what the author calls case 3. So we have bx plus c, and then x squared plus 1. Let's go ahead and multiply both sides of this equation by the denominator on the left. And we'll write the result on the next page. So after multiplying by that denominator, we get 4x on the left. On the right, a, x squared plus 1, bx plus c, all times x plus 1. And let's just go ahead and simplify this right-hand side. Ax squared plus a, bx squared, cx, bx plus c. And let's combine like terms. A plus b x squared, b plus cx. And then we have an a plus c at the very end. And now we just match the corresponding terms. On the left, we see that there is no x squared, so we can write a 0x squared here. So we have 0 equals a plus b. That's our first equation. Now for the x term, we see that it's a plus 4 on the left. On the right, it's b plus c. So we must have b plus c equals 4. And the constant term on the left-hand side is 0. And on the right-hand side, it's a plus c. So we must have a plus c equals 0. So this is a 3 by 3 system. We can go ahead and solve this for a, b, and c. So I can rewrite the first equation by solving for a. I could even take the last equation, solve it for a. And then since negative b and negative c are both equal to a, we must put these together to say b equals c. And so plugging this into the second equation, we have 2b equals 4. So that means b is 2. But then c equals 2 as well because c equals b. And finally, a equals negative c. So that's negative 2. So these are our values. So we'll go back to our partial fraction decomposition. We'll go ahead and plug in these values for a, b, and c. And then we'll write out the corresponding integral. So the integral is now, after plugging in our a, b, and c, so that's from plugging in a, and then b was 2, and then c was also 2. So that's 2x plus 2, or x squared plus 1. Let's go ahead and write this as 3 separate integrals. So negative 2 over x plus 1. Let's pull out the 2. Actually, let's not pull out the 2. We have integral 2x x squared plus 1. And then for the last integral, let's go ahead and pull out that 2. 1 over x squared plus 1. And these are integrals that we can do. For this first one here, if that plus 1 on the x is bothering you, feel free to do a u substitution. So for this first integral, this should give us negative 2, natural log, absolute value, x plus 1. For the second integral, u substitution, u equals x squared plus 1. Then du equals 2x dx. So this becomes integral 1 over u du. That's natural log, absolute value u. And so that's ln of x squared plus 1. Feel free to drop the absolute values here because x squared plus 1 is positive. And finally, for the last integral, you might remember this as being from the arctan function. We know that the derivative of tan is 1 over x squared plus 1. So that means that the integral of 1 over x squared plus 1 is tan inverse. Sorry, I forgot my inverse on the tan. But if you forgot that fact, you can go ahead and feel free to do a u sub here. X equals 1 tan theta. So using that trig sub here, this integral should become 2 tan inverse x. So the last thing to do here is just to add our 3 answers together for the integrals. So the first integral, we had negative 2, natural log, absolute value, x plus 1. Then the second integral in green, natural log, x squared plus 1. And then the last integral over here in blue, 2 tan inverse x. And don't forget that constant c of integration. And that's our final answer.